Most people, when they imagine the edge of the universe, picture a wall. Somewhere out, past the farthest galaxy, past the most distant quasar, past the last point any telescope has ever resolved, there must be a boundary, something that marks the end. And on the other side of that wall, in this picture, there is either nothing or there is some larger place the universe is sitting inside of. That picture is wrong. There is no wall, there is no outside. The universe is not the kind of object that has walls, because a wall is what a box has, and the universe is not a box. But here is what most people are not told. There might still be another side. Not past a wall, but around a loop. Walk in a straight line far enough through space itself, and if the geometry of the universe is positively curved, you arrive at a point that is as far from where you started as it is geometrically possible to be. That point is a real place. It has coordinates. It might have planets. And it is, by the physics of accelerating expansion, permanently outside the part of the universe you can ever reach. Get comfortable. Hit subscribe if this is your first time, because by the end of this, what you mean by far is going to mean something it has never meant before. Now, let's slowly ease into this. Part 1. The two pictures we carry. There is a question you have probably asked yourself at some point, maybe quietly, maybe out loud, maybe only in that drifting moment just before sleep, when the mind goes wandering across the size of things. The question is simple. What is on the other side of the universe? It sounds like the kind of thing a child would ask. And yet, when you sit with it for a few minutes, you find that the question is harder than it looked, because every honest attempt to answer it forces you to admit that you do not really know what you mean by side, and you do not really know what you mean by other, and you do not really know what you mean by universe. The words feel familiar. They have been arranged like that since you were small. But the moment you try to use them seriously, they stop working. Most people, when they reach for the answer, find one of two pictures already waiting for them. The first picture is a wall. Somewhere out past the farthest galaxy, past the most distant quasar, past the very last point of anything our telescopes have ever resolved, there is a boundary, a wall, a curtain, something that marks the end. And on the other side of that wall, in this first picture, there is either nothing or there is some other place, some kind of beyond, and outside the universe is sitting inside of. This is the picture you absorb without anyone teaching it to you. Boxes have outsides, rooms have outsides, even oceans have shores. The universe, in the first picture, is just a very large box, and the other side is whatever the box is sitting in. The second picture is the opposite. In this one, there is no wall. The universe goes on forever. You travel in any direction at any speed for any length of time, and you never reach an edge, because there is no edge. There is just more. More space, more galaxies, more emptiness, more stars and dust and dark patches. The universe in this picture is infinite, and the question of its other side is a category mistake, the kind of thing you can mouth out loud but cannot really mean, because something infinite has no other side. The other side of a thing that never ends is just more of the thing. You probably hold one of these two pictures in your head right now. You may not have noticed which one. Maybe you alternate. Maybe you have a third picture that is some hybrid of the two. But almost everyone who comes to this question comes with a model already loaded, a default they have never examined, a feeling about what the answer must be, even before they have any reason to feel anything at all. And tonight, before we go any further, I want to do something gentle but firm. I want to take both pictures away, not because they are silly, they are not silly. They are the natural way a human mind grasps something it has no senses for. But both pictures are wrong, or at minimum, both pictures are not what current physics actually says. And if we want to ask this question honestly, we have to put the pictures down first. Because here is the thing physicists figured out. Slowly, over about 100 years, working through gravity and geometry, and a long argument that began with Einstein and is still unfinished today. The universe is not the kind of object that has a side at all, not in the everyday sense. A side is what a box has, or a room, or a country. A side requires an outside. A side requires an embedding, a place where the thing is sitting. The universe, as physics describes it, is not embedded. There is no larger space it lives in. There is no room the universe is a room inside of. The four-dimensional space-time that contains everything. There is nothing else. Now, if you sit with that for a moment, you can already feel where this is going. If there is no outside, then there is no side. And if there is no side, then the question of its other side starts to dissolve. But the question does not actually dissolve. It transforms. Because there is a more honest version of the question, and that version still has answers, and the answers are stranger than either of the two pictures you walked in with. The honest version of the question is not what is on the other side of the universe. The honest version is, if the universe is curved, if it loops, if it folds back on itself the way a globe does in 2 dimensions, then there might be a point that is as far from where you are now as it is geometrically possible to be. A point on the far side of the loop, a point that is not beyond an edge because there is no edge, but a point that is at the maximum possible distance from you through the universe itself. That point is the antipode. And the antipode is what we are really asking about when we ask about the other side of the universe. So that is where we are going to spend the next 2 hours. We are going to walk slowly through what physics actually means when it talks about the universe having a shape, the strange and beautiful idea that space itself can be curved and finite without having a wall, the way the curvature is being measured right now, to the 3rd decimal place by satellites in orbit, the lower bound on how far away the antipode would have to be if the universe is closed at all, the physics fact that even if the antipode exists, no signal you send today will ever reach it. The careful searches of the cosmic microwave background that have been looking for a sign of the loop in the sky and finding nothing yet, and finally, the question of whether someone, somewhere, could be standing on the other side right now, looking back, separated from you by a gulf that no light and no thought and no message will ever cross. We are going to take the question seriously. We are going to take it apart. And by the end, the 2 pictures you came in with are going to have been replaced by something more accurate and stranger and quieter than either of them. Settle in, there is no rush. Part 2. A question decided by 3 decimal places. To make any progress with this question, we have to talk about what the universe actually is at the largest scale. Because once you see what it is made of, the question of its other side becomes much sharper. The universe is, in the language of general relativity, a 4-dimensional space-time. 3 of those dimensions are spatial. The 4th is time. The whole thing is woven together into one geometric object, and the geometry of that object is what we are really asking about when we ask if there is another side. The 3 spatial dimensions, at the very largest scale, can have one of several possible global shapes. Just 3. They can be flat, in the sense that ordinary Euclidean geometry applies, parallel lines stay parallel, the angles of a triangle add up to 180 degrees, and the geometry extends to infinity. They can be positively curved, in which case the 3 spatial dimensions wrap around on themselves, the way the surface of a globe wraps around in 2 dimensions. Parallel lines eventually converge, triangle angles add up to more than 180 degrees, and the total volume is finite. Or they can be negatively curved, hyperbolic in shape, like a saddle that goes on forever in every direction, where parallel lines diverge and triangles have angles that add up to less than 180 degrees, and the volume is infinite, but the geometry is bent in a way that flat, infinite space is not. These are the only three options, at the largest scale, under general relativity, if we assume the universe is the same in every direction and uniform when averaged across very large patches. Cosmologists call these the three Friedmann-Lemaitre-Robertson-Walker solutions, after the four people whose work in the 1920s and 30s built them. Friedmann was a Russian mathematician who died of typhoid in 1925 at the age of 37, after sketching out the equations on a notepad during a hot air balloon ascent. Lemaitre was a Belgian priest and physicist who realized the same equations independently and went on to propose the idea of an expanding universe that began from a single point, what he called the primeval atom. Robertson and Walker, working separately in 1935 and 1936, put the mathematics on a rigorous footing. Their combined work gives us the three shapes. The universe is one of these three: flat, closed, or open. And the question of its other side comes out completely differently depending on which. If the universe is flat, in the simply connected case, the version Einstein and most textbooks default to, then space extends infinitely in every direction. There is no other side, because there is no side, and there is no farthest point, because there is no farthest. The universe in that case is just infinite, and the question we asked at the top of this video has no answer that is not trivially boring. There is no other side, because the concept does not apply. If the universe is open and negatively curved, the same is true. Hyperbolic space is also infinite in extent. You can travel forever, in any direction, and never reach an end. No other side, again. But if the universe is closed and positively curved, everything changes. Then the universe is a three-dimensional sphere, what mathematicians call a three-sphere or a hypersphere, the three-dimensional analogue of the two-dimensional sphere we ordinarily call a sphere. And on a hypersphere, every single point has exactly one antipode. Walk far enough in a straight line, in any direction, and you arrive at that antipode. Walk a little farther, and you come back home. The universe in that case is finite, has no boundary, and has, for every observer, a single farthest point that is geometrically opposite to where they are. That farthest point is the answer to our question. That is the other side. And whether or not we live in that kind of universe is decided by a single number that cosmologists have spent decades trying to measure. The number is called omega sub k. It is the spatial curvature parameter. If it is exactly 0, the universe is flat. If it is positive, the universe is closed. If it is negative, the universe is open. Everything we have just talked about, the entire question of whether the universe has another side, comes down to the value of this one number. And the most precise measurement we have, from the Planck satellite combining cosmic microwave background data with baryon acoustic oscillations and supernova distances, places omega sub k at 0.001 plus or minus 0.002. That is the entire answer. To 3 decimal places, the universe is flat. To the 3rd decimal place, the universe might be slightly closed. We do not know. I want you to sit with that for a moment. The shape of the universe, the largest object that exists, the thing that contains every star and every galaxy and every empty patch of space between them, is decided by a number we have measured to 3 decimal places, and the 3rd decimal place is still telling us we might be wrong. The error bars overlap with 0. The error bars also overlap with a slightly positive value. We are right at the edge of being able to tell. The Planck satellite, launched in 2009, retired in 2013, with its data still being analysed years later, gave us the most precise measurement of the cosmic microwave background ever made. That measurement, combined with everything else we know about the expansion of the universe, gives us omega sub k equals 0.001 plus or minus 0.002, 3 decimal places. The first two are confidently 0. The third is uncertain, and in that uncertain third decimal place lives the entire question of whether the universe has another side. Future experiments are coming. The Simons Observatory, the CMB, S4 ground-based array, the Lightbird satellite from the Japan Aerospace Exploration Agency, the next generation of large-scale structure surveys from Euclid and the Vera Rubin Observatory, all of them will tighten the bounds on omega sub k over the next decade. They will push the third decimal place into a fourth, maybe a fifth. And eventually, almost certainly, within the working lifetimes of cosmologists who are alive today, we will know. Either omega sub k will be measured to be 0 to many decimal places, and the universe will be confirmed as flat or open and infinite, with no other side. Or it will be measured to be positive at high significance, and the universe will be confirmed as closed, and the answer to our question will be yes. There is another side, and the next thing we will need to figure out is how far away it is. That is where we are going next. Because if the universe is closed, the antipode is not just a mathematical possibility, it is a place. And it is a place with a minimum distance set by the same data we just talked about. And that distance, as you will see in a few minutes, is so far away that even if the antipode is real, it lives entirely outside the parts of the universe that any of us ever will be able to reach. Part 3. The Hypersphere. To understand what the other side of a closed universe actually is, we have to take a step backward and talk about something much more familiar: the surface of the Earth. Not the Earth itself, not the planet as a three-dimensional object with a core and a mantle and a crust, but just the surface, the two-dimensional skin you have walked on every day of your life. That surface has a very particular property that is so obvious to you that you have probably never noticed it. The surface of the Earth is finite, but it has no edge. Think about that for a second. You can walk in any direction for any amount of time, and you will never reach a wall. You will never reach a place where the surface ends and something else begins. The Earth's surface has a finite area. You can measure it. It is about 510 million square kilometers, and yet you can walk on it forever without falling off or stopping at a boundary. If you walk far enough in one direction, you will eventually arrive back where you started, having traveled the full circumference, about 40,000 kilometers along the equator, never once turning, never once seeing the edge. There is no edge because the surface is curved. It bends back on itself in the third dimension. From the inside, looking down at your feet, the ground feels flat, mostly. From the outside, looking from space, you can see that the whole thing is a sphere. The two-dimensional creatures who live on it would never need the third dimension to explain why their world has no edge. They could discover it from inside. They could measure the angles of a very large triangle and find that the angles add up to slightly more than 180 degrees. They could discover that two parallel lines, started at the equator and pointed due north, eventually meet at the pole. They could find that the geometry of their world is positively curved, and they could conclude that their world wraps around on itself, even without ever leaving the surface. Now imagine the same trick in 3 dimensions. Imagine that the 3-dimensional space you live in, the space you walk through, the space your bedroom is in, the space the galaxy occupies, is also curved. Not curved in any one direction, curved in the same way the Earth's surface is curved, just 1 dimension higher. Curved so that if you walked in a perfectly straight line in any direction for long enough, you would eventually arrive back where you started. Curved so that the whole thing has a finite volume but no boundary. Curved so that, just like the 2-dimensional creatures on the surface of the Earth, You could not point to where the universe ends, because it does not end, it bends. A three-dimensional space with this property is called a three-sphere or a hypersphere. The mathematicians who study it write it as S3. The two-sphere, S2, is the surface of an ordinary ball. The three-sphere is the next dimension up. You cannot picture it directly, not in the way you can picture a basketball, because picturing it will then go seeing in 4 dimensions. Your visual cortex was not built for that. But you can reason about it. Every property of the two-sphere has a three-sphere analog. The two-sphere has a center, sitting in the 3rd dimension, that the surface curves around. The three-sphere has a center, sitting in a 4th dimension, that our 3-dimensional space curves around. The two-sphere has a finite area. The three-sphere has a finite volume. The two-sphere has the property that every point has an antipode, the point on the surface that is exactly opposite, exactly through the center of the ball. The North Pole's antipode is the South Pole. New York's antipode is somewhere in the southern Indian Ocean, several hundred kilometers off the coast of Australia. The three-sphere has the same property. Every point has an antipode, the point exactly diametrically opposite through the 4th dimensional center, the point that is, in the strict geometric sense, as far away as it is possible to be without coming back around. This is the answer the universe is allowed to have to our question, if the universe is closed. There is an other side. The other side is the antipode of where you are sitting right now. It is the single point in the universe that is geometrically farthest from your chair. Walk in any direction in a perfectly straight line, the kind of straight line that follows the curvature of space, and you will eventually arrive at that point. Keep walking, and you will come back home. The universe in this case is finite. It contains everything. There is nothing outside it, because there is no outside. There is no embedding space. The 4th dimension that I just used to help you visualize the curvature is a mathematical convenience, not a physical place. The hypersphere does not need to sit inside anything to exist. The curvature is intrinsic. 2-dimensional creatures on the surface of a sphere can detect the curvature of their world from inside, without ever knowing about the 3rd dimension. We can do the same. The curvature of our 3-dimensional universe is something we can measure from inside, and we are measuring it, and the measurement is right on the edge of telling us that we live on a hypersphere. Now I want you to do the thought experiment with me. I want you to be the 2-dimensional creature on the globe for a few minutes, because the analogy is the cleanest way to feel what is going on, and I want you to feel it before we move on to the numbers. You are a small, flat, 2-dimensional being. Your body has length and width, but no height. You live on the surface of a sphere. The sphere is large enough that, walking at a comfortable pace, you cannot see its curvature directly. The ground under your feet looks flat. The horizon is the same distance away in every direction. You walk forward, the ground stays flat. The horizon stays where it is. You walk for an hour, for a day, for a year. The ground is still flat. The horizon is still there. You have never seen a wall. You have never seen an edge. As far as you can tell from your immediate surroundings, you live in an infinite flat plane. And then, after walking long enough, you arrive back where you started. You did not turn. You did not bend your path. You followed the straightest possible line your 2-dimensional world allows, and that line brought you all the way around the surface and back to your starting point. You realize, in that moment, that your world is finite. It has a definite size, it has a definite area, and yet it has no edge. There is no wall anywhere. There is no place where the world ends. You discovered the curvature from inside by walking far enough, and here is the kicker, the part that maps directly onto our question. While you were walking, halfway through your journey, you passed through a point that was as far from your starting position as it was geometrically possible to be, the antipode, the other side of the sphere, the single point on your two-dimensional world that was exactly opposite where you started. You did not notice anything special when you passed through. The ground was still flat under your feet. The horizon was still the same. It was, in every local respect, just another point. And yet, in the larger geometry of your world, it was the farthest you could ever get from home. Now scale this up by 1 dimension. You are a 3-dimensional being. You live in a 3-sphere. You walk in any direction. The space around you looks flat. Local geometry behaves the way Euclidean geometry behaves, more or less. Triangles have angles that add up to 180 degrees, plus or minus a tiny correction that depends on the size of the triangle relative to the size of the universe. You walk forward. The horizon, if there were one, stays the same distance away. You walk for 1 billion years at the speed of light. And eventually, if you have walked long enough along a straight line, you arrive back where you started. Halfway through your trip, you pass through the antipode of your starting position. You did not notice. The local geometry was the same. The stars looked normal. But you were, at that moment, on the other side of the universe. That is what the other side of the universe is, if the universe is closed. It is the antipode on the hypersphere. It is a real point in real space. It is a place with coordinates. It is the single point in the universe at the maximum possible distance from your chair. There is, in this picture, a kind of cosmic flaw under everything we mean by far. Far is finite. Far has a ceiling. The ceiling is the antipode. You cannot get any farther from home than that, no matter how long you walk. What does the antipode look like if you were standing there? Local geometry would tell you nothing unusual. The space around you would look like ordinary space. There would be stars and dust and dark patches. There might be galaxies. There might, if the universe is rich enough at every scale, be planets and life and other observers. You would not know you were at the antipode of anything. The point is special only in relation to your starting position. From the antipode of the antipode is your home. You would have to walk around the universe to find that out. There is no marker that says here is the other side. The other side is the other side only relative to where you came from. And this is the thing that takes a moment to digest because it cracks open the original question. There is no single other side of the universe. There is an other side relative to every observer. For every chair, every star, every patch of empty space, there is a single antipode, the point as far away as it is possible to get. Your antipode is somewhere out there. Your antipode's antipode is back here. The universe, in this picture, is a structure of pairs. Every point has its opposite. Every observer has theirs. The 2-dimensional analog that I keep coming back to has one more lesson before we move on. On the surface of the Earth, the antipode of the North Pole is the South Pole. They are both points. Neither is the edge of the world, neither is the outside. Both are just places. The North Pole does not look at the South Pole and see something strange or terrifying. It sees just another part of the same world. The 2 poles are connected by every meridian. Walk any longitude line, you will get from one to the other. The same is true on the hypersphere. The antipode is not strange. It is just another point. It is connected to your home by every geodesic. Walk in any direction long enough, you will reach it. The universe, in the closed picture, is a single connected place where every point is at most 1/2 of one loop away from every other point. This is a very different universe from the one most people walk around imagining. It is not infinite. It is not enclosed by walls. It is finite and edgeless. It has a maximum size. It has a maximum farthest distance. It has, for every point, a single other side that is as opposite as it is possible to be. And whether or not we live in this universe is, as we just talked about, decided by a number that is currently being measured. Omega sub k, the third decimal place. The next decade or two of cosmology may settle this. Until then, the antipode lives in the math and in the data, right at the edge of what we can detect. Before we go to the question of how far away the antipode would have to be, I want to do one more thing, because the geometry is going to keep mattering for the rest of this video. I want to make sure the picture in your head is solid. The closed universe is not a box. It is not a balloon expanding into a room. It is not a snow globe with a glass shell. It is a self-contained, edgeless, finite geometry whose curvature wraps it back on itself. The dimensions are intrinsic. The shape is intrinsic. There is no outside. There is no embedding. The mathematical fourth dimension I use to help you picture the curvature is a tool, not a place. There is no room the universe is sitting in. There is the universe, and the universe is everything. And on it, if it is closed, every observer has an antipode. And the antipode is the other side. Hold that picture. We are going to use it. Part 4. The lower bound. So the universe might be closed. The antipode might exist. The next question, the one that makes the abstract concrete, is how far away it would have to be. And here the data we already have, the same Planck measurements we talked about earlier, give us a hard floor. The antipode, if it exists, cannot be closer than a certain minimum distance. That minimum is bounded by the same number that decides whether the universe is closed in the first place, omega sub k. The closer to 0 omega sub k is, the larger the closed universe has to be, the farther away the antipode would have to be, and the harder it would be to ever see any direct sign of the loop. Right now, the data places omega sub k very close to 0, which means that if the universe is closed at all, it is closed on an enormous scale. The calculation was done carefully in 2011 by a team at the University of Oxford. The lead author was Mihran Vardanyan. His co-authors were Roberto Trotta and Joseph Silk, two of the most respected cosmologists in the world. Silk in particular has been working on the structure of the universe since the 1960s and is one of the people whose career has spanned almost the entire history of modern cosmology. The team published their analysis in the monthly notices of the Royal Astronomical Society Letters, volume 400.13, page L91. They took the best Planck precursor data and supernova data available at the time, ran a careful Bayesian analysis under the simplest inflationary priors that physicists assume for the early universe, and asked the following question. If the universe is closed, what is the lower bound on its curvature radius? The answer they got was striking. At 99% confidence, the conformal radius of curvature of the universe has to be at least 251 times the radius of the observable universe. 251. That is a multiplier. The observable universe has a co-moving radius of 46.5 gigalight years, which is the distance to the farthest light we can see, accounting for the expansion of space during the light's journey. Multiply 46.5 by 251, and you get just over 11,700 gigalight years. That is the minimum curvature radius of the closed universe, if the universe is closed. The loop circumference, the distance you would have to walk along a straight line to return to your starting point, is 2 times pi times the radius. 2 times pi is roughly 6.28. Multiply that by 11,700, and you get about 73,300 gigalight years. That is the minimum circumference. The antipode is halfway around the loop, which means the minimum distance to the antipode is about 18,300 gigalight years. 18,300 gigalight years. Let me say that number a few different ways, because numbers like this tend to slide off the mind, and the whole point of this section is to make the distance feel real. The observable universe is 46.5 gigalight years across. The minimum distance to the antipode is about 18,300 gigalight years. So the antipode, in the closest possible closed universe, is roughly 400 times farther than anything we have ever seen. Anything. Every galaxy, every quasar, every distant patch of cosmic microwave background, every photon that has ever reached an Earth-based telescope or a satellite has come from inside the 46.5 gigalight-year radius of the observable universe. The antipode, if it exists, is at least 400 times farther than that. The volume ratio is even larger. If you cube the linear ratio, you get the volume ratio. 400 cubed is 64 million. The closed universe, in the closest possible case, is at least 64 million times the volume of the observable universe. In some Bayesian estimates, that number reaches 10 million as a conservative lower bound from the original Vardanyan-Trotter-Silk paper. Either way, the universe is, at minimum, vastly larger than the patch we can see. Most of it, in this picture, is hidden from us. Most of it always will be. And this is just the flaw. The actual universe, if it is closed, could be arbitrarily larger. The Vardanyan-Trotter-Silk bound is the smallest closed universe consistent with current data. The actual closed universe could be 10 times larger than that, or 100 times larger, or 1,000. We have no upper limit on the size of a closed universe. We only have a lower limit. The data is consistent with closed universes of any size, from the minimum upward all the way to effectively infinite, which means the antipode, if it exists, could be 18,300 gigalight years away, or it could be 1,000,000 times that, or more. The honest scientific position is that we know the minimum and we have no idea about anything beyond it. I want to stop for a moment and let this sit. The observable universe is the patch of the cosmos we can directly study. It contains roughly 2 trillion galaxies. By current estimates, 2 trillion. Each galaxy contains, on average, 100 billion stars. So the patch of the universe we can study contains, very roughly, 200 sextillion stars, 2 followed by 23 zeros, stars. And the closed universe, in the smallest possible case, contains at least 64 million times that, 12 octillion stars, in the closed minimum. That is 1 followed by 28 zeros. The number of stars in the smallest closed universe is so large that the number of stars in the observable universe rounds to 0 by comparison. And almost all of those stars are forever beyond our reach. They live in the part of the universe that we cannot see, cannot probe, cannot study. They have orbits and lifespans and supernovae and gravitational waves and possibly civilizations, and not a single photon from any of them will ever reach a telescope on Earth. They are real, in the closed picture, and they are unreachable. They are the inhabitants of the other side, if other side is the right phrase, which it is not, exactly, because the other side is not a single location, it is a hemisphere, it is the entire half of the loop that is past the antipode from us. The antipode is the geometric maximum of distance. Everything from a little past the observable universe outward is, in the closed picture, on the other side, in some looser sense, 251 times the radius of what we can see, 64 million times the volume, 12 octillion stars, and not one of them ever within our reach. This is what the data forces us to acknowledge, if the universe is closed. The closed universe is large. The closed universe is mostly hidden. The closed universe contains, almost by definition, more than we can ever know about. And the question of the other side stops being a question about a single point and becomes a question about an entire half of a structure that is so much bigger than the visible part that the visible part barely counts as a sample. There is a sentence I want to give you to carry through the rest of this video, because it is the sentence the data forces. The universe might be a place that exists in the geometry, but not in the physics. The closed universe, in the lower bound case, is a real place in the math. It has a definite size, it has definite contents, it has an antipode, and almost none of it is reachable by any physics we know. Hold that phrase, we will come back to it. A place that exists in the geometry, but not in the physics. That is what the other side of the universe, in the strict sense, might be. We will see in the next section exactly what unreachable means, because the geometry is not the only thing that hides the antipode from us. The expansion of the universe is doing its own job, and that job is to close the door on the antipode in a way that is even more permanent than distance alone. Part 5. The door that closes on its own. Up to now, we have been talking about distance, as if distance were the only thing that mattered. The antipode is far away. Far enough away that no telescope can resolve it. Far enough away that no probe could ever reach it. But the truth is even harsher than that. And the harsher truth comes from a piece of physics that most people are not taught when they learn about the universe in school. The universe is expanding, and the expansion is accelerating. And the acceleration creates a boundary around every observer in the cosmos, beyond which no signal sent today can ever arrive. That boundary is called the cosmic event horizon. And it is the door that closes, on its own, on the question we are asking. Let me explain what that boundary is, because it is the central piece of physics in this whole video, and it tends to get confused with other boundaries that sound similar. There are several different kinds of horizon in cosmology. The Hubble sphere, the particle horizon, the event horizon, the observable universe. They are all different. They are all measured in light years. They are all distances that depend on the expansion of space in some way. And they tend to get conflated in popular accounts, which makes the actual physics harder to grasp. So I want to walk through them carefully. The Hubble sphere is the distance at which the recession velocity of objects, due to the expansion of space, equals the speed of light. That distance is currently about 14.4 gigalight years. Inside the Hubble sphere, space is expanding slower than light can travel. Outside the Hubble sphere, space is expanding faster than light can travel. This used to be taught as the boundary of what you could ever signal, because intuition suggests that if space is expanding faster than light, then no light signal can cross it. That intuition is wrong, and the correction is one of the great clean-up jobs in cosmology, done definitively by Charles Lineweaver and Tamara Davis in their 2004 paper in Publications of the Astronomical Society of Australia, Volume 21, page 97. The Hubble sphere is not the same as the event horizon. Light from beyond the Hubble sphere can, under certain circumstances, still reach us, if the expansion decelerates in the future, or if the proper distance closing rate eventually overtakes the recession. The Hubble sphere is not the door. The particle horizon is the distance light has had time to travel since the Big Bang, accounting for the expansion of space during the journey. That distance is the radius of the observable universe, 46.5 gigalight years. Inside this radius, everything is in principle observable. Light from those objects has had time to reach us. Outside this radius, nothing is observable yet. The particle horizon grows over time, because as the universe ages, light from farther sources finally arrives. It is the past-facing boundary. It tells us what we can see right now. It is not the door. The cosmic event horizon is the future-facing boundary. It is the distance at which an object is, right now, just barely close enough that a signal we send today, at the speed of light, will eventually reach it. Send a signal toward an object farther than the cosmic event horizon, and it will never get there, because the space between us and the object is expanding faster than the signal can close the distance, and the expansion is accelerating. Under the standard cosmological model, with the Hubble constant at 67.4 kilometers per second per megaparsec and the dark energy density at 0.685, the cosmic event horizon is at a proper distance of 16.59 gigalight years from any observer. 16.59, give or take 0.18, that is the door, and the door is closing. Not metaphorically, literally. Under accelerating expansion driven by dark energy, the cosmic event horizon is shrinking. The volume of the universe inside which we can ever influence anything is contracting in proper distance over cosmic time. Galaxies that are currently just inside the horizon are slipping across, becoming permanently unreachable, becoming part of the universe we can still see but can never affect. The trip is one way. Once a galaxy crosses out, it stays out. The horizon will continue shrinking over the next several tens of billions of years until eventually, in the very far future, the cosmic event horizon will encompass only our local supercluster, and the rest of the universe, including every other galaxy we can currently see, will be on the wrong side of the door. Now think about what this means for our question. The antipode, if the universe is closed, is at least 18,300 gigalight years away. The cosmic event horizon is 16.59 gigalight years. The ratio is more than 1,000 to 1. The antipode lives outside the event horizon by a factor of more than 1,000, which means that no signal sent from here, today, in any direction, at any speed, up to and including the speed of light, can ever reach the antipode. Not in a billion years, not in a trillion years, not in any finite time at all. The geometry might place the antipode somewhere in space. The physics of expansion forbids contact. This is the moment I want you to sit with, because it is the central reality shift of this video. The antipode is not far in the sense that it is hard to reach. It is not far in the sense that we have not built fast enough ships. It is not far in the sense that future civilizations might one day cross the distance. It is far in a way that physics has made permanent. The accelerating expansion of the universe has placed the antipode outside our causal future, and no engineering, no technological progress, no theoretical breakthrough that does not violate the equations of general relativity can change that. The door is shut. The door was shut by the geometry of space-time under dark energy. The door cannot be reopened. I want to do an immersive passage with you here, because the abstract version of this fact is hard to feel, and I want you to feel it. Imagine you are standing on a high plateau, on a planet, in a galaxy, somewhere near the edge of the observable universe. You have in your hand a perfect light source. You point it in the direction of where the antipode is, and you turn it on. A pulse of light leaves your light source, moving at exactly the speed of light, traveling in a straight line along the curvature of space, headed toward the antipode of your galaxy. The light begins its journey. For the first few billion years of its journey, the light travels through space that is expanding at a rate slower than the light is moving. The light makes net progress. It crosses billions of light years. It moves further from you, closer to its destination. You watch the light go. Then the light begins to cross regions where the expansion of space is faster than the speed of light itself. Now, the light is still moving forward, still going at exactly the speed of light through the local space around it. But the space around it is itself moving away from the antipode faster than the light can keep up. The destination is racing away from the light. The light is racing forward. The gap, in absolute proper distance, begins to grow. The light is still moving. The light has not slowed, but the destination is getting farther away in real time. The light will never catch up. You watch from the plateau. You can no longer see your own light beam, of course. It is too far away. But you know it is out there. You know it is still traveling. You know it will travel for the rest of time, forever, never arriving. The pulse exists. The destination exists. The geometry of space-time forbids them from meeting. There is a signal that exists in space-time, and a destination that exists in space-time, and the geometry forbids them from meeting. That is the closest description I can give you of what unreachable means in physics. The two objects are both real. The path between them exists. The walking of the path is not allowed by the rules of how space-time evolves under accelerating expansion. The light will travel for eternity and never make the trip. That is the antipode. That is what we are talking about when we ask what is on the other side of the universe. If the universe is closed, it is a place that exists in the geometry but not in the physics. The math says it is there. The physics says no contact, no signal, no observation, no influence, no information, ever. A complete and permanent severance by the rules of how space-time behaves under dark energy. Hold that phrase one more time before we go on. A place that exists in the geometry, but not in the physics. The other side of the universe, if it exists, is exactly that kind of place. And here is the part that gets under the skin. The part that is hardest to digest. The part that I think is the real reason this question feels so strange to ask. The geometry permits the existence of the antipode. The physics forbids contact. Both are simultaneously true. We do not get to pick one. The universe, if it is closed, has both properties at once. There is a place that is real, that exists, that has coordinates, that may contain stars and planets and observers, and we are barred from ever knowing anything about it by the same physics that makes the universe expand in the first place. The thing that drives galaxies apart and accelerates the expansion of space is also the thing that locks the antipode away from us. It is not an accident of distance. It is a structural feature of how space-time evolves under dark energy. The other side is closed off the same way the universe expands. The two facts are the same fact, in different language. That is the door. That is the door closing. That is the universe deciding, through its own physics, what is and is not knowable. The antipode is on the wrong side of that decision. So is anything else more than 16.59 gigalight years away from where you are sitting? The vast majority of the universe, if the universe is closed, has been placed beyond contact by the geometry of dark energy, and the closing of the door is accelerating. It will continue to close for the rest of the universe's history. There is no scenario in which it opens back up, short of dark energy reversing its behavior in some way our current physics does not predict. In the next section, we are going to talk about how cosmologists actually look for evidence that the universe is closed at all. Because everything I have just told you depends on the assumption that the curvature is real, that omega sub k is not exactly zero, that the universe has a loop, we have not confirmed any of that. We have a measurement at the edge of detection. We have lower bounds on what the loop must be like if it exists. We have a door that closes either way, but the loop itself, the actual physical fact of a closed universe, has not been settled. And the way cosmologists have tried to settle it is by looking at the oldest light in the universe, the cosmic microwave background, and asking whether the loop has left a fingerprint anywhere in the sky. Part 6. The search in the oldest light. If the universe is closed and the loop is small enough, the loop should leave a fingerprint somewhere in the sky. The fingerprint would be in the cosmic microwave background, which is the oldest light in the universe. The microwave background is the leftover radiation from when the universe was about 380,000 years old, the moment when the universe had cooled enough that atoms could form and photons could finally travel freely instead of being scattered by free electrons. Before that moment, the universe was opaque. After that moment, it was transparent. The cosmic microwave background is the photograph of the boundary between the two. It is the most ancient image we have. It is uniform to about 1 part in 100,000 across the entire sky. It is, in every direction we look, almost exactly the same temperature, just under 3 degrees above absolute zero. And it carries, encoded in its tiny temperature fluctuations, the structure of the early universe. If the universe is closed and small, light from the antipode of our position on the last scattering surface should make a complete trip around the loop and arrive back at us, but coming from the opposite direction. This produces a very specific signature. The same patch of physical space should appear in our sky from 2 opposite directions, once from in front and once from around the back. The temperature pattern of that patch, encoded in the microwave background, should be identical in both views. If you draw the right circle on the sky in one direction and the corresponding antipodal circle in the opposite direction, the temperature pattern around each of those 2 circles should match, point for point. This prediction was made precise by Neil Cornish, David Spergel, Glenn Starkman, and Eiichiro Komatsu in 2004 in Physical Review Letters Volume 92, page 201302. The 4 of them set up the mathematical framework for what they called the matched circles test. The idea was simple. If the universe is small and closed, the cosmic microwave background sky should contain pairs of antipodal circles whose temperature patterns are correlated. The size and orientation of the circles depend on the size of the universe and the geometry of the loop. The Cornish team developed an algorithm that could scan an entire microwave background sky for these matched pairs. They applied the algorithm to the data from the Wilkinson Microwave Anisotropy Probe, the WMAP satellite, which had just finished its first full year of observation. They scanned for matched circles at every plausible size and orientation. They found nothing. Their result placed a lower bound on the size of the universe. If the universe has a non-trivial spatial topology, a topology that loops back on itself at any scale, then its smallest fundamental dimension must be at least 1.2 times the diameter of the observable universe. The diameter of the observable universe is about 93 gigalight years. Multiply by 1.2 and you get a minimum smallest dimension of about 112 gigalight years. The universe could still loop back on itself. It just had to loop on a scale at least that large. The Planck collaboration extended the analysis in 2015 using data from the Planck satellite, which was a successor to WMAP with significantly higher precision. They published their topology analysis in Astronomy and Astrophysics, volume 594, paper A18. They tightened the bound. They looked for matched circles, matched pairs of points, and the specific signatures predicted by every standard compact topology, the 3 torus, the slab space, the chimney space, the Poincaré dodecahedral space, and several more exotic candidates. They found no matches. The Planck data is consistent with a universe whose loop, if it loops at all, is larger than the patch of universe we can directly observe. This is an important result, but it is worth being careful about what it does and does not say. The search rules out the smallest topologies. It does not rule out closed universes that are large. It does not rule out a hypersphere whose curvature radius is large enough that the loop circumference is many times the diameter of the observable universe. The Vardanyan-Trotter silk bound we talked about in the last section applies here too. The minimum curvature radius of a closed universe is more than 250 times the observable radius. That kind of universe would not show matched circles in the cosmic microwave background because the antipodal point would be far outside our last scattering surface and the loop would not close within our line of sight. The matched circles search rules out small, closed universes. It is silent on large, closed universes. the large closed universe remains entirely possible. There is another, more speculative prediction worth talking about, because it has shown up in real papers and in real searches. In a closed three-sphere universe with a small enough loop, the antipode would not appear as a pair of matched circles. It would appear as a single point smeared across the entire sky. Light from the antipode, traveling outward in every direction, would converge on us from every direction simultaneously. The antipodal image, in such a universe, would be a kind of ghost halo, an apparent diffuse source that occupies every line of sight. This is the closed universe equivalent of standing at the South Pole on Earth and looking up to see every line of longitude converging back at the North Pole. There is, in principle, an antipodal sky image. We have searched for it. We have not seen one. The Luminet team, led by Jean-Pierre Luminet at the Paris Observatory, working with Jeffrey Weeks, Alain Riazuelo, Roland Lehoucq, and Jean-Philippe Uzan, proposed a very specific small universe model in 2003 in Nature, volume 425, page 593. They proposed that the universe might be a Poincaré dodecahedral space. A dodecahedron is a 12-sided three-dimensional figure, each face a pentagon, the kind of shape used as a 20-sided die's relative. The Poincaré dodecahedral space is a closed three-dimensional space whose fundamental domain is a dodecahedron, with each face identified with its opposite face. The space has positive curvature and a finite volume. The Luminet team noted that this geometry made specific predictions for the largest scale temperature patterns in the cosmic microwave background, and they thought the WMAP data, at the time, matched those predictions reasonably well. The low quadrupole moment, the unexpectedly small amplitude of the largest temperature variations in the background, fit the dodecahedral space prediction. Subsequent searches with more precise data have not confirmed the Luminet model. Cailleri, Lachiez-Ray, Luminet, Lehoucq, Riazuelo, and Weeks refined the predictions in 2007 in Astronomy and Astrophysics, volume 476, page 691. Rukema, Bulinski, Shaniewska, and Gaudin in 2008 ran a dedicated search for antipodal matched circles at the dodecahedral space scale in Astronomy and Astrophysics, volume 486, page 55. They found nothing significant. The Luminet model is not ruled out exactly because the searches probe specific predictions and the model has some freedom in its parameters, but the natural fit has not held up under closer examination. The model is no longer mainstream. It is still active in the literature. It is a serious proposal that has not been confirmed. So the punchline of the matched circles search, and of the topology search more generally, is this. The universe might still be closed. The universe might still have an antipode. But if it does, the loop is at least as large as the patch of universe we can see, and the antipode is at least as far away as the lower bounds we have already talked about. The cosmic microwave background has not given us a direct image of the loop. The fingerprint, if it is there, is too faint or too far. We have looked, we have not found. There is one more thing about the matched circles search worth saying. Cosmologists tend to describe a null result as a constraint rather than a refutation, because a closed universe with a loop circumference much larger than the observable patch would also produce a null result. The data is consistent with a flat, infinite universe, and it is also consistent with a closed universe whose loop is larger than our line of sight. These two possibilities cannot be distinguished by the matched circles test alone, because the test specifically probes the case where the loop is small enough to image, a larger loop is invisible to the test. The honest position is that the matched circles search has ruled out a particular class of small closed universes, and the remaining options are all consistent with the data we have. This kind of result, a null result that simultaneously rules out one possibility and leaves several others open, is the texture of modern cosmology. We are not in a regime where the data points unambiguously at one answer. We are in a regime where the data narrows the space of possibilities, slowly, decimal place by decimal place, and the question of whether the universe is closed is going to be one of the slowest questions to settle. The next generation of cosmic microwave background experiments, the next generation of large-scale structure surveys, the next generation of gravitational wave standard sirens that might pin down the Hubble constant independently will all push on omega sub k. Eventually, if the universe is closed, we will see it. If the universe is flat, we will know that too. Until then, the Antipode lives in the data at the very edge of detection, and the match circle search is the most direct experimental probe we have, and it has come back empty. So, we have closed off the small universe option, mostly. We have not closed off the large universe option. And the large universe option is the one that is hardest to feel, because in that option, the antipode is real, and it is real on a scale so far past the visible patch that the patch barely counts. That is where the next section is going to take us. We are going to look at the menu of topologies that are still possible, and we are going to see that even within the closed universe answer, there is more than one way for the universe to fold back on itself. There are several different shapes a closed universe could be, and each shape gives a slightly different answer to what is on the other side. Part 7. The menu of shapes. The hypersphere is not the only way for a universe to be closed. It is the most familiar way, because the two-dimensional analog, the surface of a globe, is something we can all picture. But the mathematics of three-dimensional manifolds is richer than that. There are several distinct shapes a closed three-dimensional space can have, and each shape changes what other side actually means. The simplest alternative is the three-torus. A torus, in 2 dimensions, is a donut shape, a surface that loops in 2 independent directions. The three-torus is the 3-dimensional version. It is a finite 3-dimensional space in which moving in any of 3 independent directions eventually brings you back to where you started. The classic visualization, the one that everyone with a mathematical bent has seen at some point, is a video game like Asteroids or Pac-Man. The screen wraps around. Walk off the right side, and you appear on the left. Walk off the top, and you appear on the bottom. The game world is, topologically, a 2-torus. You can travel in any direction forever, but the world is finite, and if you walk in a straight line in any one of 2 independent directions long enough, you come back to your start. The 3-torus does the same thing in 3 dimensions. Walk far enough in the x direction, and you come back. Walk far enough in y, and you come back. Walk far enough in z, and you come back. There is no curvature in a 3-torus. Locally, the geometry is perfectly flat, but globally, the topology is non-trivial. 3 independent loops, 3 independent ways the universe wraps around. In a 3-torus universe, your antipode is no longer a single point. It is more like 3 different antipodes, one along each axis of the loop. Or, more accurately, the antipode is a region that depends on the geometry of the fundamental domain, the smallest piece of the universe that, repeated and tiled, builds the whole space. In a rectangular 3-torus, the antipode could be defined as the point at the center of the opposite face of the fundamental domain. In a more exotic 3-torus, the antipode could be more complicated. The point is that the 3-torus universe is closed and flat, and it has antipodal structure, but the antipodes are organized differently than they are on a hypersphere. The 3-torus has been a serious candidate for the shape of the universe for decades. It is one of the simplest, closed flat manifolds. It is consistent with all current data as long as the fundamental loop in each direction is large enough that the matched circles search would have missed it. The Cornish team in 2004 and the Planck collaboration in 2015 both included 3 torus topology in their searches. Both came back with the same conclusion. The smallest fundamental dimension of a 3 torus, if the universe is 1, must be at least 1.2 times the diameter of the observable universe. Beyond that, the data is silent. The 3 torus could be exactly at the lower bound, or much larger. There are other compact, flat manifolds beyond the 3 torus. Mathematicians have classified them. There are exactly 10 different ways for 3-dimensional flat space to close up into a finite manifold, with different identifications of opposite faces. The Klein bottle-like shapes, the half-turn space, the quarter-turn space, the chimney space, the slab space. Some of these involve reflections and rotations when you cross a boundary, which produces strange effects. In a half-turn space, for example, if you walk forward long enough, you arrive back at your start, but rotated by 180 degrees. Your left hand is now on what was your right. The universe in that case is closed, flat, and chiral. It treats orientation differently in different places. These exotic topologies are real possibilities. They are consistent with all current data. They predict slightly different patterns in the cosmic microwave background. None of those patterns have been detected. Each of them has been ruled out at small scales by the topology searches. None of them have been ruled out at large scales. The universe could be any one of them, or it could be a hypersphere, or it could be flat and infinite. We do not know. There is one more option I want to mention, because it has had a strange and recurring role in cosmology over the last 20 years. The Poincare dodecahedral space. This is a closed 3-dimensional manifold with positive curvature. It is not a hypersphere. It is a quotient of a hypersphere by a particular discrete group of symmetries. The fundamental domain is a dodecahedron, a 12-sided figure with pentagonal faces. The opposite faces of the dodecahedron are identified after a 36-degree rotation. The resulting space is closed, has positive curvature, has finite volume, and has antipodal structure that is different from both the hypersphere and the 3 torus. In a Poincare dodecahedral space, there are effectively 12 antipodes, one through each face of the fundamental domain. The space has a particular symmetry that produces a recognizable signature in the cosmic microwave background. The Luminet team, the same team I mentioned in the last section, proposed that the universe might be a Poincare dodecahedral space based on the observation that the low quadrupole moment in the WMAP data fit the prediction of such a space well. The fit, in 2003, looks surprisingly good. The further data from Planck has not confirmed it. The low quadrupole anomaly is real, but the dodecahedral space prediction has not held up under more precise measurement. The model is still active in the literature, but it is no longer considered the most likely shape. It is on the menu. It is not the leading candidate. Now I want to take a step back, because this menu is not just a mathematical curiosity. It matters for what other side actually means. In the hypersphere case, every point has exactly one antipode. The other side is a single place. In the 3 torus case, there are multiple antipodes, one per axis. The other side is several places. In the Poincare dodecahedral case, there are 12 antipodes. The other side is 12 places. Each shape changes the answer to the question we asked at the top of this video. And in every case, the antipode or antipodes are far enough away that they are outside the cosmic event horizon. The same physics that locks the hypersphere antipode at 18,300 gigalight years away locks the 3 torus antipodes and the dodecahedral antipodes outside our causal future as well. The closed universe is large in any of its compact forms, and the door is shut in every case. The variety of shapes is real. The unreachability is universal. Whichever topology the universe has, if it has a closed topology at all, the antipodes are real geometric places that exist outside the patch of universe we can ever influence. This is the menu. This is what physics actually says about the possible shapes of the universe at the largest scale. The mainstream answer is that we do not know which one. The data is consistent with several. The data is also consistent with none, with a flat, infinite universe whose only other side is more of the same. There is no preferred answer in modern cosmology. There are bounds, and there are searches, and there are predictions, and there is honest uncertainty. The menu is open. But I want you to hold on to one thing as we move forward, because it is the thread that ties this whole video together. Whichever shape the universe has, if it has a closed shape, the other side is not abstract. It is not metaphor. It is a real place with real coordinates and possibly real contents. It is a place that exists in the geometry. And it is, in every closed topology, consistent with current data, a place that exists in the geometry but not in the physics. The unreachability is built into the structure of the answer. Whichever shape we eventually settle on, if any, the antipodes are going to be on the wrong side of the door. In the next section, I want to slow the pace down. I want to take you to one of those antipodes, if you will let me. I want to put you, imaginatively, on the far side of the loop. We have done the geometry. We have done the data. We have done the physics. Now I want to do the experience. I want you to feel what it would be like to stand at the antipode of where you are right now, on a closed universe consistent with everything we know, and to look back toward where home should be, to see, or not see, what is there, to understand from the inside what the other side actually means. That is where we are going next. Part 8. Standing at the Antipode. I want you to do something with me. I want you to put down whatever you are holding, settle into wherever you are. Close your eyes if you can. Stay listening, but let your body soften. And let me take you, in your imagination, to a place that is real in the geometry and unreachable in the physics. You are at the antipode of where you are sitting right now. The universe is a closed hypersphere. Its loop circumference is just at the lower bound that the data permits, about 73,300 gigalight years around. You have been transported by the magic of imagination to the single point in the universe that is geometrically opposite your home, 18,300 gigalight years away, through the loop in the strict geodesic sense. You are standing on the surface of a planet. The planet has gravity. The planet has a sky. The planet circles a star. The star is part of a galaxy. The galaxy is part of a local group, part of a supercluster, part of a filament in the cosmic web. All of it sitting on the backside of the hypersphere, the side of the loop that is as far from your home as the geometry allows. You are at the antipode. You look up, the sky is dark. The local stars of the galaxy you are on are bright, scattered across your view in the same way the Milky Way is scattered when you look up from a dark site on Earth. You can see thousands of them. They cluster into the disk of your antipodal galaxy. They form a band of light across the sky, a river of stars, exactly the way our own galaxy does. The galaxy here looks like a galaxy. The night looks like a night. You turn your head and look in the direction your home is supposed to be. There is nothing visible from there. Not nothing in the sense that there are no stars in that part of the sky. Because there are stars, the local stars of your antipodal galaxy fill that direction the same as every other direction, but nothing in the sense that there is no light from home. The Milky Way is invisible. It is not faded. It is not dim. It is not a distant smudge that with a good telescope you could resolve. It is, in the absolute sense, not there to be seen. The reason is the cosmic event horizon. The light that left the Milky Way at the moment you, the listener, were born, has been travelling for a few decades now. It has gotten as far as a few tens of light years from the Milky Way. The Antipode is 18,300 gigalight years away. The light from the Milky Way has not even crossed 1/millionth of the distance it would need to cross to reach you here, and it never will. The space between the Milky Way and the Antipode is expanding faster than light can cross it. The photons from home are in flight, moving forward, never arriving. They will be in flight forever. They will never reach this point, not in a trillion years, not in any time. The geometry permits a path from there to here. The physics forbids the path from being walked by any signal. You stand on the antipodal planet, and you understand, for the first time, what unreachable actually means. It does not mean far. It does not mean hard. It means that two places exist in space-time, with a path between them, and the path cannot be traversed because the road itself is dilating faster than the traveller. You are at one end of the road. Home is at the other. The road is real. The walking of the road is not allowed by the rules. You turn around. You face the direction opposite from home. You face the sky in the other half of your view. There are stars there too. Different galaxies. Galaxies you have never seen on any photograph, in any astronomy book, in any telescope image, because none of them are inside the patch of universe that any descendant of yours, at any time, can ever observe. They are the inhabitants of the other side of the universe, from your perspective at the Antipode. They are the universe past the Antipode, from where home used to be. They are another sphere of unreachability, just like the one you came from. This is perhaps the part of the picture that is hardest to digest, so I want to take it slowly. From the Antipode, the universe in every direction is roughly the same. There is a finite patch you can see. There is an event horizon at 16.59 gigalight years, in every direction, beyond which signals cannot be sent. There is an antipode for the Antipode, which is your home, and around the antipode of the Antipode, there is another event horizon, another 16.5 gigalight year sphere, beyond which lies, again, unreachable universe. The closed universe is a sphere of sphere, an onion of causal patches, each patch with its own door closing. From every point in the universe, the antipode of that point is on the wrong side of every door. The geometry is symmetric. The unreachability is everywhere. You stand on the Antipode planet, and you understand, slowly, that this is the structure of a closed universe under accelerating expansion. There is no privileged center. There is no privileged edge. Every observer is equally locked into their patch. Every observer has an antipode they cannot reach. Every observer is, from someone else's perspective, the antipode they cannot reach. The universe is a place full of pairs, each pair forever separated by space too big to cross. The geometry of the hypersphere holds them all together as a single connected space. The physics of dark energy holds them apart as causal patches that will never overlap. Now, I want to do one more thing here, because the experience is not complete without it. You are still standing at the Antipode. You look up at the sky one more time. You aim, in your mind, at where home is, even though you cannot see it. You imagine a beam of light leaving the planet where home is, this very moment, racing toward you. The light is in flight. It will be in flight forever. It will never reach you. But the light is still real. The light left. The light is traveling. The light exists in space-time as a particular trajectory, an actual line through the geometry of the universe, with a beginning and a direction and a wavelength. It will keep moving forever, getting closer to your position in some sense and farther from your position in another sense, depending on how you measure. In any time slice you pick, the light is somewhere. It is real, and it will never arrive. This is the closest I can get you, in words, to the experience of the Antipode. There is a signal that exists in space-time, and a destination that exists in space-time, and the geometry forbids them from meeting. Hold that phrase one more time. We have used it twice now. We will use it once more before we finish. It is the central physical fact of the closed universe answer. Stay with me here, at the Antipode, for one more moment. Look back toward home one more time. Even though you cannot see it, recognize that, in every meaningful sense, you are someone else's antipode. The same physics that locks home away from you, locks you away from home. Someone might be standing on a planet there, at home, doing exactly what you are doing, looking back across an unreachable gulf, separated from you by space too big to cross. Same loop, same hypersphere, same universe, same expansion, same age, same physical laws, same impossibility of contact, ever, by any physics yet known to either of you. Two halves of the same universe, drifting apart faster than light can keep up, connected by geometry, severed by physics. Hold that picture. This is what the other side of the universe is, if the closed answer is correct. Not a wall, not nothing. A place with planets and stars and possibly observers. A place you cannot reach. A place no signal you send today will ever arrive at. A place that exists in the geometry and not in the physics. Open your eyes if you close them. You are back wherever you were. You are at home. The antipode is out there somewhere, in the closed picture, at the maximum geometric distance. Or there is no antipode, in the flat picture, and the universe is infinite and the question dissolves into more of the same. Either way, you have, for the last few minutes, been to the other side of the universe. You have stood at the geometric maximum of distance. You have looked back at home and not seen it. You have understood, viscerally, what unreachable means in the strongest sense the laws of physics permit. In the next section, we are going to come back to the data, because the question of which universe we live in, the closed one with the antipode or the flat one without, is not just a question for thought experiments. It is a question that the cosmic microwave background is, right now, being squeezed for an answer to. There are anomalies in the data. There are patterns in the largest scale temperature variations that mainstream cosmology cannot fully explain. They may be statistical noise. They may be the first whispers of a topology we have not yet measured. Either way, they are sitting in the data as you and I have this conversation, and they deserve to be heard out. Part 9. Anomalies in the oldest light. The cosmic microwave background is one of the most thoroughly measured signals in all of physics. It has been mapped by Kobe in 1989, by WMAP from 2001 to 2010, by Planck from 2009 to 2013, by ground-based telescopes at the South Pole and in the Atacama Desert, and by balloon experiments at the edge of the atmosphere. Every map has shown the same basic picture, a nearly uniform glow at about 2.725 degrees above absolute zero, with tiny temperature fluctuations at the level of 1 part in 100,000, distributed in patterns that match the predictions of standard inflationary cosmology almost everywhere we look. Almost everywhere. There are a few places where the data does not quite match the predictions, and the mismatches have been there since the WMAP era. They have been confirmed by Planck. They have not gone away with more precise measurements. They have not been explained. They are real features of the data, sitting at the edge of statistical significance, and a small but persistent group of cosmologists has spent the last 20 years asking whether they are noise or whether they are the first faint signatures of something the standard model of cosmology is missing. We are going to walk through 3 of them, because each one connects, at least loosely, to the question of the universe's shape. The first is the suppressed quadrupole. The quadrupole moment of the cosmic microwave background is the largest spatial pattern in the temperature data, the simplest non-uniform variation across the whole sky. It is what you would see if you smoothed the temperature map until only the largest scale features remained. Inflationary cosmology predicts a specific amplitude for this quadrupole based on the spectrum of primordial density fluctuations. The actual measured quadrupole is lower than that prediction, not dramatically lower. The deviation is around 2 standard deviations, give or take, depending on which analysis you use. Not enough to overturn the model, but persistent. The same low quadrupole appeared in COBE data, was confirmed by WMAP, and was confirmed again by Planck. It has been there for more than 3 decades. It has not gone away. The second anomaly is the axis of evil. This name was coined by Kate Land and João Magejo in a 2005 paper in Physical Review Letters, volume 95, page 071301. The phrase referred to the surprising alignment of the lowest spatial harmonics of the microwave background. The quadrupole and the octupole, the 2 largest spatial patterns in the data, have axes of symmetry that are aligned with each other much more closely than would be expected from random statistical fluctuations. The combined alignment is at greater than 3 standard deviations. Even more strangely, the axis appears to be aligned with the ecliptic plane and with the dipole direction, the direction of our motion through the cosmic microwave background frame. These are local features of our solar system and our galaxy. They have no business showing up in the largest scale patterns of the cosmic microwave background, which originates from a sphere 13.8 billion years away. The alignment is probably coincidence. It might be an instrumental artifact. It might be a feature of large-scale topology that the standard model does not capture. The honest answer is that nobody knows. The pattern is in the data. The explanation is not. The third anomaly is the cosmic microwave background cold spot. This was first identified in WMAP data by Patricio Vielva, Enrique Martinez Gonzalez, and collaborators in 2004 in the Astrophysical Journal, volume 609, page 22. It is a region in the southern hemisphere of the sky, in galactic coordinates around 209 degrees longitude and minus 57 degrees latitude, where the cosmic microwave background temperature is anomalously low. The patch is about 10 degrees across, a substantial chunk of sky. The temperature deficit is about 70 microkelvin. The statistical significance is around 3.5 standard deviations. Planck confirmed the cold spot in its 2014 analysis in Astronomy and Astrophysics, volume 571, paper A23. The cold spot is real. The explanation is still being debated. Several proposed explanations have been put forward. The most mundane is that the cold spot is a statistical fluke. The cosmic microwave background contains many tens of thousands of independent spatial features at this scale. With enough features, you expect a few to deviate substantially from average just by chance. The cold spot might be one of those few. The probability is small, but not negligible. The mundane explanation is on the table. A second proposed explanation involves a foreground effect, a large void in the nearby universe that produces a slight cooling of the background by the integrated Sachs-Wolf effect. A 2017 study by Istvan Sapudi and collaborators identified the Eridanus supervoid, a huge underdense region in the line of sight toward the cold spot. The void could partially account for the temperature deficit, but most analyses find that the void is not large enough to fully explain the anomaly. The mismatch remains. A third explanation, the speculative one, involves large-scale topology or a primordial feature in the early universe. Marcos Cruz, Neil Turok, Patricio Vielva, Enrique Martinez Gonzalez, and Michael Hobson proposed in a 2007 paper in Science, volume 318, page 1612, that the cold spot might be a cosmic texture, a topological defect in the inflationary field, a kind of localized scar from the very early universe. The texture interpretation is consistent with the data, but is not preferred by most cosmologists because cosmic textures are predicted by certain symmetry-breaking phase transitions that have not been independently confirmed. Nevertheless, the proposal exists in the literature. It has not been refuted. Each of these anomalies, taken individually, sits at the edge of significance. None is decisive. None is widely accepted as evidence of a topology or a closed universe or a non-trivial geometry. Mainstream cosmology treats them as statistical noise, plausible deviations within an otherwise excellent fit. But the same handful of anomalies has shown up consistently in every cosmic microwave background dataset for more than 2 decades. They have not been smoothed out by better data. They have, if anything, become more precisely measured. Their existence is not in dispute. Their meaning is. There is a way of looking at this that I want to share, because it is the honest scientific position. The cosmic microwave background is consistent with a flat, simply connected, infinite universe. It is also consistent, in the presence of these few anomalies, with a closed universe of large but finite size. The flat universe interpretation has fewer free parameters. The closed universe interpretation requires a specific topology and a specific size. By the standard of Occam's razor, the flat universe wins. By the standard of explaining every feature of the data, neither wins decisively. Cosmologists overwhelmingly favor the flat universe as the default, because it is simpler. But the door is not closed on the closed universe. The anomalies, if they are anomalies and not noise, are pointing somewhere. Where they are pointing, nobody knows for sure. I want to be careful here, because this is exactly the kind of topic that gets distorted in popular accounts. The anomalies in the cosmic microwave background are real, but they are not proof of anything. The axis of evil is not evidence of a flat Earth-style cosmic conspiracy. The cold spot is not a portal to another dimension. The low quadrupole is not a sign that the universe is broken. These are statistical features of the largest scale temperature pattern in the oldest light in the universe, features that deviate from the standard model's predictions at the few sigma level and that have not yet been explained by any mainstream mechanism. They may turn out to be noise. They may turn out to be physics. The data does not yet decide. What I will say, and this is the thread that ties this section to the rest of the video, is that the anomalies are exactly the kind of signature you would expect to find first if the universe were closed and large. If the loop circumference is just past the lower bound of the match circle's search, the most direct topology probes will come back null, as they have. But the influence of the loop on the very largest spatial scales of the cosmic microwave background, on the quadrupole and octopole, might still leak through. The anomalies might be the first whispers. They might also be nothing. The honest answer is that we are at the edge of what current measurements can resolve, and the next decade of experiments will either firm up the anomalies into a clear signal or smooth them out into noise. In the meantime, the data sits where it sits. The largest patterns in the oldest light may or may not be telling us something the standard model is missing. Whatever they are telling us, if anything, the message has been there for more than 3 decades, in every map, getting more precisely measured each time. The universe is whispering. Whether we can hear it is a question of better instruments and patience. There is one more piece of data from the local universe that deserves a section because it is the most direct candidate we have for a signal from beyond the observable patch. It is called dark flow. It is contested. It is unresolved. And if it is real, it is the closest thing we have to a tap on the shoulder from the other side of the universe. That is where we are going next. Part 10. Something pulling from outside. In 2008, a team of astronomers, led by Alexander Kashlinsky at the NASA Goddard Space Flight Center, published a paper that, if it holds up, is one of the most consequential cosmological observations of the last 50 years. The paper appeared in the Astrophysical Journal Letters, volume 686, page L49. The team had analyzed the motions of distant galaxy clusters, hundreds of them, scattered across a substantial fraction of the sky and extending out to roughly 1 billion light-years. They had used a technique called the kinetic Sunyaev-Zeldovich effect, a tiny distortion of the cosmic microwave background that occurs when its photons scatter off hot electrons in a moving cluster. By measuring the distortion in carefully chosen directions, they could infer the bulk motion of the clusters relative to the cosmic microwave background frame. What they found was startling. The clusters were not moving randomly. They were moving coherently in a single preferred direction at speeds of 600 to 1,000 kilometers per second. The flow was statistically significant. It extended out to the limit of their sample. It pointed roughly toward the constellation Centaurus in the southern sky, and it could not be explained by the gravitational influence of any mass distribution inside the observable universe. The standard cosmological model predicts that bulk motions at this scale should be small, a few hundred kilometers per second at most, decreasing with distance. The Kashlinsky team was seeing motions that were larger than predicted, and that did not decrease with distance, and that pointed in a single coherent direction. They named the effect dark flow. The interpretation they proposed was striking. The dark flow, in their reading, could be the gravitational fingerprint of mass distributions outside the observable universe, beyond the horizon, in regions of space that we cannot directly see. If something massive enough is sitting beyond the boundary of what we can observe, its gravitational pull would influence the motion of clusters inside the observable universe. The clusters would respond to a mass distribution they cannot see, and the response would look like a coherent bulk flow in a preferred direction. The dark flow, if real, is a gravitational signal from the other side. This interpretation is significant for the question we have been asking, because it would be the most direct empirical evidence that there is anything past the boundary of the visible universe to even talk about. Not just geometric possibility, not just topological consistency, an actual physical influence, measurable from inside our patch, originating from mass distributions outside our patch. If the dark flow is real, the other side of the universe is not just a place we can deduce from geometry. It is a place that is reaching across the boundary and pulling. The interpretation, however, is highly contested. Almost from the moment Kashlinsky's paper came out, other teams began reanalyzing the same data and reaching different conclusions. The Planck collaboration published a major analysis in 2014 in Astronomy and Astrophysics, volume 561, paper A97. They used the higher precision Planck data and a more careful treatment of the kinetic Sunyaev-Zeldovich signal. They found no statistically significant bulk flow at the scales Kashlinsky had reported. Their analysis suggested that the original detection was either a statistical fluctuation or an artifact of systematic errors in the WMAP era data. The Planck collaboration's conclusion was that dark flow, as originally claimed, is not present in the better data. The Kashlinsky team disputed the Planck analysis. They argued that the Planck team's masking procedures, the way they had excluded certain regions of the sky from the analysis, had removed exactly the signal they were claiming to look for. The Kashlinsky team continued to publish follow-up papers throughout the 2010s, refining the measurement, extending it to larger samples of clusters, and consistently finding a bulk flow. Their numbers shifted slightly. The direction stayed roughly the same. The amplitude remained in the range of several hundred kilometers per second. As of the most recent analyses, the question is unresolved. Some teams report a dark flow signal at statistical significance. Other teams report no signal. The two camps are using overlapping datasets, similar techniques, and reaching opposite conclusions. The community has not converged on an answer. The mainstream view, if there is one, is cautious skepticism. The signal has not been confirmed by independent groups using independent techniques. The systematic uncertainties are large. The interpretation, even if the signal is real, is speculative. But the possibility that dark flow is real, and that it is a gravitational influence from beyond the observable universe, is one of those scenarios in cosmology that is too important to dismiss outright, even if the data is ambiguous. If it is real, it would be direct empirical evidence that the universe extends beyond our visible patch. It would say something specific about the distribution of mass on the largest scales. It would suggest that the inflationary epoch, the brief period of exponential expansion in the very early universe, left a slight inhomogeneity in the distribution of matter at scales larger than the observable horizon. That inhomogeneity would not be predicted by the simplest inflationary models, but it would be permitted by some variance. The Mersini-Houghton and Holman proposal, in a 2008 paper in the Journal of Cosmology and Astroparticle Physics, suggested that pre-inflationary inhomogeneities could produce exactly this kind of signal if certain conditions in the very early universe were met. The proposal is speculative. The data, as we have said, is contested. I want to be careful here because dark flow is the kind of result that gets oversold in popular accounts. The honest position is this. The original detection was made by a credible team using a sound technique. The result has not been independently confirmed. Subsequent analyses with better data have come back with mixed conclusions, with the Planck collaboration leaning toward no detection and the Koszlinski team continuing to report a signal. The community is divided. The mainstream view is that dark flow is probably not real, but it has not been firmly ruled out. The next decade of large-scale structure surveys, especially the ones that will use independent techniques to measure cluster motions, will likely settle the question one way or the other. If dark flow is real, the implications are profound. The other side of the universe, in that case, would not just be a geometric possibility, it would be a physical influence. Something, somewhere, beyond the horizon, is pulling on the visible patch with enough force to set hundreds of galaxy clusters moving coherently in a single direction. That something could be a mass distribution from before inflation, a fragment of the pre-inflationary universe that retained its inhomogeneity. It could be a fluctuation at the scale of the multiverse, if the multiverse exists, with our universe sitting near the edge of a larger structure. It could be the gravitational influence of an unseen part of a closed universe, with the loop bringing distant mass distributions into contact with our patch through the curvature itself. None of these is a settled interpretation. All of them are consistent with the original signal, if the signal is real. This is one of those open questions in cosmology that I find genuinely thrilling, not because I know the answer, but because the answer matters. If dark flow is confirmed, it changes what we are talking about when we ask what is on the other side of the universe. It moves the question from pure geometry into observable physics. The other side becomes, in that case, not just a place, but a place with measurable gravitational influence on us. The string between us and the other side goes taut. Something is pulling. We can feel it. We just have not been able to confirm that the pull is real. Until then, the dark flow sits in the literature as an unresolved anomaly, like the cold spot, like the axis of evil, like the low quadrupole. A signal that might or might not be telling us something the standard model is missing. A whisper that might be noise, might be physics, might be the first hint of what lies past the horizon. The dark flow, if it is real, is the closest thing we have to a fingerprint of the other side. If it is not real, it is one more null result in a long history of looking for signs of structure beyond what we can see. Either way, it deserves to be acknowledged. It deserves to be heard out. There is a sentence in the Koszlinski 2008 paper that I have always remembered. The team wrote that the dark flow, if real, points towards something beyond our cosmic horizon. They did not claim to know what that something is. They did not commit to an interpretation. They reported the data, and they noted what the data would mean if it held up. That is the right tone. That is the cosmological position when you are at the edge of what your instruments can resolve, and the data is telling you something you cannot yet make sense of. You report the signal. You leave the interpretation open. You let the future of cosmology decide. In the next section, we are going to widen the picture one more time. We have spent most of this video inside the closed universe answer, the hypersphere and its variants, the antipode and its unreachability, the cosmic microwave background search and its anomalies. But the closed universe is not the only answer mainstream physics has put forward to the question of the other side. There are other frameworks, each with their own version of what other side means, and the menu of serious physics options is broader than just compact topology. We are going to walk through the alternatives. Part 11. The other answers. The closed universe answer, the hypersphere with its antipode, is one way physics can say something about the other side of the universe. It is the cleanest answer. It is the one most directly tied to the data we have. But it is not the only answer, and a complete treatment of the question requires walking through the alternatives, because each one carries a different picture of what other side might mean. I want to walk through 4 of them. Eternal inflation, the Hartle-Hawking no-boundary proposal, conformal cyclic cosmology, and brane-world cosmology. Each is a serious physics framework. Each has been worked out in detail by physicists whose names you might recognize. Each gives a different answer. The first is eternal inflation. This idea grew out of the inflationary cosmology framework developed by Alan Guth in 1981, refined by André Linde and Paul Steinhardt and Andreas Albrecht in 1982 and 1983. The basic claim of inflation is that, in the first tiny fraction of a second after the Big Bang, the universe underwent a period of exponential expansion driven by a high-energy scalar field. Inflation solves a number of cosmological problems, including why the cosmic microwave background is so uniform and why the universe is so close to spatially flat. The standard version of inflation lasts a fraction of a second and ends. The eternal version, proposed by Linde in 1986 in Physics Letters B, Volume 175, page 395, says that inflation never globally ends. The energy field that drives inflation is unstable in the sense that small regions of it decay into ordinary matter and energy, producing what we call big bangs. But the inflation continues in the regions that have not yet decayed. The result is an eternally expanding background in which bubble universes nucleate and grow inside the inflating sea, each one becoming its own little patch of ordinary expanding spacetime, surrounded by inflating regions that recede faster than any traveler can ever cross. In this picture, our universe is one bubble in an eternally inflating sea. From inside our bubble, the bubble looks infinite. The interior of a bubble nucleated in eternal inflation has the geometry of an open hyperbolic 3-space, which appears infinite to any observer inside. The bubble wall is past every observer's cosmic event horizon. We cannot see it. We cannot reach it. But it is out there, in this framework, separating our bubble from the inflating background. The other side of the universe, in eternal inflation, is something different from the antipode. It is another bubble. Another universe, just like ours, nucleated in another patch of the inflating sea, with its own bubble wall and its own internal geometry. The other bubbles are out there. They are receding from us, the inflating background carrying them away faster than light can keep up. They will never be reached by any signal from ours. They are unreachable in the same strict sense. The closed universe antipode is unreachable, but for a different geometric reason. The bubble universes are not antipodes on a loop. They are siblings in a parent metastructure. The other side, in this picture, is hierarchical. It is one level up in a nested structure, and there are not just two halves of the universe. There are infinitely many bubbles, populating the inflating background in some pattern we cannot directly observe, each one with its own physics, its own particle content, possibly even its own values of the fundamental constants. The second framework is the Hartle-Hawking no-boundary proposal, published by James Hartle and Stephen Hawking in 1983 in Physical Review D, Volume 28, page 2960. Their proposal addressed the question of what the universe looked like at the very beginning, at the moment of the Big Bang. Standard general relativity says that the universe began with a singularity, a point of infinite density where the equations break down. Hartle and Hawking proposed something different. They proposed that the universe has no boundary in either time or space. The Big Bang, in their picture, is not a singular starting point, but a smooth geometric transition, like the North Pole on a globe. North of the North Pole, the question does not apply. South of the North Pole is the rest of the globe. The no-boundary proposal makes the universe a closed four-dimensional geometric object with no singular boundary anywhere. In this picture, the question what is on the other side of the universe takes on a strange new meaning. If the universe has no boundary in any direction, then asking what is on the other side is like asking what is north of the North Pole. The question is geometrically ill-formed. There is no other side because the universe simply closes up smoothly in every direction. Not in the sense that it loops back on itself in a hypersphere, but in the sense that the geometry curves into itself in a way that makes other side a category error. The universe, in the no-boundary picture, is everything. Asking about its outside is like asking about the outside of a sphere from the inside of a sphere. The question presupposes something that does not exist. This is a profound answer, and it has the virtue of being mathematically clean. The Hartle-Hawking no-boundary proposal has been influential precisely because it dissolves the singularity problem without adding extra structure. The cost is that it makes the other side question malformed. The universe simply is. There is nothing outside. There is nothing past the loop. The question dissolves. The third framework is conformal cyclic cosmology, developed by Roger Penrose and described most fully in his 2010 book, Cycles of Time. Penrose proposed that the universe goes through an infinite sequence of phases, each of which he calls an aeon. Each aeon begins with a Big Bang and ends, in the far future, in a state of maximum entropy where all matter has decayed, all black holes have evaporated, and the only remaining structure is electromagnetic radiation. Penrose noticed something mathematically curious. In the far future, after all massive particles have decayed away, the universe has no rest frame anymore. There is no way to define a meter or a clock. The geometry becomes conformally invariant, meaning that the scale of distances loses meaning. Penrose argued that this scaleless far future of one aeon is mathematically identical to the infinitesimal Big Bang of the next aeon. The far future of an aeon hands off conformally to the Big Bang of its successor. In this picture, the other side of the universe is a previous aeon, a whole prior universe, with its own history, its own galaxies, its own civilizations, whose conformal far future was our Big Bang. And our far future, billions of years from now, after all the stars have died, will be the conformal Big Bang of the next aeon. The universe, in this framework, is a chain. Each aeon is connected to the next. The other side is a previous link. Penrose and his collaborator, Vahe Gurzadyan, claimed in 2010 and again in 2013, and again in 2018, to have found possible signatures of prior eons in the cosmic microwave background. They identified what they called Hawking points. Small temperature anomalies, they argued, were the conformally rescaled signatures of supermassive black holes that had evaporated in the previous aeon. The claim is controversial. It has been disputed by other cosmologists in technical replies. The evidence is not conclusive. But the framework remains a serious proposal in theoretical cosmology, and it gives a specific, structured answer to what is on the other side of the universe. The other side, in conformal cyclic cosmology, is the previous eon, and the universe is an infinite chain of eons stretching forward and backward without end. The fourth framework is brane-world cosmology. This is the most exotic of the four, and it comes from string theory and certain higher dimensional models of gravity. The basic idea is that our three-dimensional universe is a brane, a kind of membrane embedded in a higher dimensional bulk spacetime. Other branes might exist, separated from ours by a small distance in the extra dimensions. The most concrete version is the ekpyrotic and cyclic cosmology proposed by Paul Steinhardt and Neil Turok and their collaborators in a series of papers starting in 2001. They propose that the Big Bang was the result of a collision between our brane and another brane, and that this collision happens periodically, generating an infinite sequence of Big Bangs along our brane's history. In this picture, the other side of the universe is another brane, a whole separate three-dimensional universe, parallel to ours, separated by an extra dimension we cannot directly experience. The other brane is not at the antipode of a hypersphere. It is not a bubble in an inflating sea. It is not a previous aeon. It is a parallel sheet of three-dimensional space-time sitting in the higher dimensional structure that contains both branes. The other side, in this framework, is laterally adjacent, just across a dimension we cannot perceive. The honest assessment of these four frameworks is that none of them is confirmed. Eternal inflation is consistent with much of modern cosmology, but has no direct empirical confirmation. The Hartle-Hawking proposal is mathematically elegant, but does not make predictions that are easily testable. Conformal cyclic cosmology has some claimed signatures in the cosmic microwave background, but these are disputed. Brane-world cosmology is part of the larger string theory framework and has not produced any unambiguous experimental signatures. Each is a serious idea. None is the standard model of cosmology. The standard model of cosmology, LCDM, is silent on what is on the other side of the universe. It assumes a flat universe out to the limits of measurement, and it does not commit to any particular global topology or higher dimensional embedding. So we are left, as we so often are in modern cosmology, with a menu of possibilities and no clear winner. The closed universe with its antipode, eternal inflation with its bubbles, the no-boundary proposal with its dissolved question, conformal cyclic cosmology with its chain of eons, brane-world cosmology with its parallel branes. Each is a different answer. Each has a different texture. Each leaves a different aftertaste when you sit with it for a while. The question of what is on the other side of the universe has, in modern theoretical physics, more than one acceptable answer. The data does not yet pick between them. The question is open. In the final section of this video, I want to bring all of this back to where we started, to the listener, to the chair, to the question as it was originally asked, in the simple form, the one a child might ask. And I want to leave you with what I think is the most honest summary of where we actually stand. Not a tidy conclusion, not a clean answer, but a recognition of where the question lives in current physics, and of what it means for you, sitting where you are, that the question has the shape it has. Part 12. A place that exists in the geometry. We have come a long way from the two pictures we started with, the wall at the edge of the universe the infinite sea that has no other side. Both of those pictures, you can see now, were shorthand. They were the mind's way of grasping something it had no senses for. The real answer, the one current physics actually permits, is stranger than either, and quieter, and more uncertain, and more beautiful, in a way that is hard to put into a single sentence. So, I am going to try anyway. The universe might have an other side. The universe might not. The shape parameter omega sub k, measured to 3 decimal places, says we cannot yet tell. If the universe is flat or open, there is no other side in any meaningful sense. The universe is infinite and unbounded, and the question dissolves into more of the same. But if the universe is closed, if the 3rd decimal place tips positive, then there is an antipode. There is a single point on the far side of the loop, 18,300 gigalight years away, in the smallest closed universe, consistent with the data, and more in any other. That point has coordinates. That point exists in the geometry. And that point is, by the physics of accelerating expansion, permanently outside our causal future. The door closed on it billions of years ago, and the door is closing further with every second of cosmic time. The other side, in that case, is a place that exists in the geometry, but not in the physics. I have used that phrase 3 times now. I want you to keep it. It is the most precise summary of what current cosmology says about what is past the boundary of our knowable universe. There is geometry past the boundary. There is no physics-accessible path to get there. The math allows the destination. The dynamics forbid the journey. Both are true at once. What does that mean for you, sitting where you are? It means several things, and I want to be careful about each of them. It means that, if the universe is closed, you have an antipode. There is a point as far from your chair as the geometry of space-time allows. At that point, planets and stars and possibly observers might exist. The geometry permits it. The local physics there would be exactly the same as the local physics here. The same gravity, the same quantum mechanics, the same elements, forged in the same kind of stellar interiors from the same kind of Big Bang. Someone could be there. The universe, in its closed form, is large enough and uniform enough that the same conditions that produced you here could, in principle, produce someone there. You have an antipode. So might they. It means that you and your antipode, if your antipode exists, share a universe and live in separate causal futures. You will never receive a signal from them. They will never receive one from you. The space between is expanding faster than light can cross it, and the expansion is accelerating. The separation is permanent. 2 halves of the same universe, drifting apart faster than light, can keep up, connected by geometry, severed by physics. Same loop, same hypersphere, same laws, no contact ever. It means that the question we asked at the top of this video has, in current physics, a structured answer that is not a definitive answer. The answer is that there might be an other side. The other side might be the antipode of a hypersphere, or the antipodes of a 3 torus, or the 12 antipodes of a dodecahedral space. The other side might be another bubble in an eternally inflating sea. The other side might be a previous aeon in conformal cyclic cosmology. The other side might be a parallel brane in brane-world cosmology. The other side, in some frameworks, is geometrically ill-formed and the question dissolves. There are several serious physics answers. The data does not yet pick between them. The honest scientific position is that we know enough to ask the question carefully and not enough to answer it definitively. And it means that the question is, for the time being, one of those open questions that may or may not be resolved in your lifetime. The next decade of cosmic microwave background experiments will tighten omega sub k. The next generation of large-scale structure surveys will probe topology. The next gravitational wave detectors will measure the Hubble constant independently and either resolve the Hubble tension or make it worse. Cosmologists working today, in 2026, are looking at the same data we have been talking about, and they are designing the experiments that will, over the next 20 to 50 years, push the third decimal place into a fourth, maybe a fifth. Eventually, the answer will firm up. Either the universe will be confirmed flat to many decimal places, and the other side will dissolve as a question, or omega sub k will tip positive at high significance, and the antipode will become a real geometric fact of the universe we live in. Either way, the question will move from the edge of detection to a settled answer in the working lifetimes of cosmologists who are alive now. Until then, the universe sits where it sits, right on the edge, right at the third decimal place, right where the question is most interesting because the answer has not yet been chosen. I want to leave you with one last image because I think it is the truest one I can give. You are sitting in your chair, somewhere out beyond your bedroom wall, beyond your house, beyond the city, beyond the planet, beyond the solar system, beyond the galaxy, beyond the local group and the supercluster, beyond the cosmic microwave background, beyond the cosmic event horizon, beyond the limit of what any signal you ever send could possibly reach. There is, if the universe is closed, a point. The point is the antipode of where you are. The point has coordinates that depend on the loop circumference of the universe. The point is real in the geometry. The point is unreachable in the physics. Light from you, leaving your home today, is racing toward that point and will never arrive. Light from that point, if it was emitted long ago in the same direction, has been racing toward you for billions of years and is still in flight, will be in flight forever, and will never arrive. A signal exists in space-time, and a destination exists in space-time, and the geometry forbids them from meeting. Hold that image. It is the closest description I can give you of the other side of the universe, if the closed answer is correct. A point that exists, and that you cannot reach. A place that exists in the geometry, and not in the physics. And then, gently, let the image go. Because the alternative is also possible. The universe may be flat. The universe may be open. The universe may have no other side at all. In which case, the question we have spent 2 hours on dissolves, and the answer is just more universe in every direction, more stars, more galaxies, more empty space, with no special point and no maximum distance and no antipode for anyone. That is also possible. That is also consistent with the data. The third decimal place could go either way. You are in a universe whose shape is being measured in real time by satellites and ground-based telescopes and balloon experiments and gravitational wave detectors, by people whose careers have been spent on this single question. And the answer is not yet in. The other side of the universe, if it exists, is permanently outside your reach. And whether it exists at all is something we will learn together, slowly, decimal place by decimal place, over the next handful of decades. Settle into wherever you are. The universe is a strange place. The largest patterns in it are being measured in real time. The question of whether there is anything past the edge of what we can see is one of the most beautiful and unresolved questions in all of cosmology. We are alive at a moment when the answer is finally beginning to come into focus. That is enough for tonight. Sleep well. Let the question stay where it is, at the edge of detection, where the universe keeps it. We will be here again soon, walking through another corner of the same strange and beautiful structure that contains us. Until then, the other side, if it exists, is out there somewhere, with its own night sky, its own stars, its own quiet planets in their own orbits. We will not visit. We will not signal. We will only know eventually, whether it is real. And that, for now, has to be enough.